So I've tooled this system up with some gauges in the case drain line coming out of the motor. I put in an inline flow meter so we can actually watch the case drain flow. It should give us some indication of the motor's health normally, because we assume as case drain leakage goes up that there's more leakage in the motor. However, in this type of system, because of the flushing shuttle and the full flushing system, we're going to see kind of prescribed leakage that isn't going to give us much indication of the motor's health at all. It's going to give us more of an indication of how much oil is being flushed through by the flushing shuttle and flushing relief. But we'll measure that, and it'll give us an indication of how the flushing system's doing, and also give an indication that the charge pump is in fact producing enough flow, because if we see the flow here, we know its original source, what's putting back in the system is the charge pump. I've also put pressure gauges in both sides of the drive loop here at the flushing valve, just because we have those handy spots where there's easy tapping in for pressure. So we'll be able to see our forward and reverse drive pressure, and we'll be able to see charge pressure and neutral on both of these gauges. What I didn't do is put a flow meter in the main drive loop. If I did, and I have it in the past, we'd see about 45 gallons per minute flow rate, which is a little bit odd, because if you look at the length of these hoses and the size of the motor and the pump, you know there's no 45 gallons in there. So probably what you have is more like 2 gallons, going around 22.5 laps a minute. So you can kind of imagine the speed that oil travels in a hydrostatic drive loop when you do see the flow. So if we got 45 gallons a minute here and we got 2 gallons of oil, even that might be a stretch. But if we got 1 gallon of oil, that means it's going around 45 times a minute. So if you followed a molecule of oil, it's pretty much doing a lap here in a 1 or 2 seconds. So the characteristic whining sound that closed loop hydrostatic circuits make has a lot to do with just the speed that the oil's going. And again, you really have to be concerned about cleanliness, because when you get a particle of sand in the oil going that type of speed, it becomes obviously very abrasive to the system. And with only 1 or 2 gallons of oil going around here over and over and over and being recycled in its purpose, obviously it's going to generate a lot of heat. So that's where that flushing shuttle and flushing relief come in and try and flush heat out through the flow meter. So measuring case drain flow on a system like this is imperative to know it's operating well. So I've started up the electric motor with our control in the neutral position. So the swash plate, we got a servo control that's controlling the swash plate via the 2 servo cylinders to hold it steady in the flat position, so there's no displacement to the pump. So it's not pumping either direction in the high pressure lines. But the charge pump, of course, is fixed displacement. It's turning, it's pumping oil in through the 2 charge check valves, charging up the hoses on either side of the drive loop right to the motors. And because we've got the gauges in here, we can see the pressure on either side of our drive loop. So we're seeing about 225, 230 psi. The reason they're reading a little different is just the calibration of the sensors themselves. But they're essentially reading charge pressure. So what we're seeing right now is the setting of our charge relief valve, our neutral charge relief valve, as John Deere would call that. So that charge relief is controlling how much pressure gets pushed into both of these hoses. And so that's how we can check charge pressure. Some machines will give you a separate charge pressure tap for checking it, but we don't really need that. We can check charge pressure right in our drive loop hoses. As long as we're in neutral, we know that we're just charging up the system. If I look at my flow meter in the case drain line, the puck is right down, it's reading 0 GPM. And that's because I've got the same pressure on either hose. The flushing shuttle in here is in the middle position where it's not flushing into the flushing circuit at all. So we don't have any, and of course the motor's not leaking because it's not turning, so we don't have any case drain flow as would be expected. I'm just going to ease the control into forward here, and we'll watch the shaft on the motor. So the motor's now turning. The transmission here is our load, and load-induced pressure on the forward side, about 600 psi right now. Transmission's not driving anything, so it's fairly low. On the reverse side, we've got about 200 psi. So what's happened there is oil's coming in to drive the motor. We're seeing the pressure at one of the gauges on this side. The other side, we're reading charge pressure, and that's dropped about 20 psi from where it was before, because this charge relief is no longer controlling charge pressure. Now it is this charge relief, our flushing relief in the block on the motor, is now controlling our charge pressure, because on the low side of the drive loop, the flushing shuttle is shifted, so that low side pressure now has access to the flushing relief. So instead of 225, 230, we're reading 200 charge pressure. If I go into reverse, go back to neutral, see our two charge pressures go back to the neutral charge setting. When I go in reverse, we see our high pressure on the opposite gauge, and again we see our flushing relief setting on the opposite gauge. Every time I go back to neutral, I go back to the same neutral charge relief value. If I watch my flushing flow meter, case drain flow meter off the motor, and I go forward, I see the case drain flow go up. We'll watch the motor turn. The case drain flow is increased. Go back to neutral, watch the puck. And then when I go to reverse, so we're seeing the puck jump up there in either reverse or forward. And that's just an indication that our flushing shuttle valve is shifting, because there's a difference in pressure. When these two pressures are unequal, then the flushing shuttle is going to shift, pushed by the pressure differential, and then that's going to start indexing flow from the whichever side of the motor is the return side through the flushing relief into the motor case drain line. So we're going to see that puck jump up every time we go forward and reverse. Every time we hit neutral, you see the puck drop back down. And our flushing flow out the motor case looks to be just around 3 gallons per minute. Just picking up the speed here, seeing what sort of pressures we get on the gauges. So going to an abrupt forward. The transmission's causing about a 1700 psi load there. Every time I go abruptly into forward. Then once the rolling mass of the transmission starts to get some inertia, rolling inertia, that pressure drops back down.